Hello and welcome. In this video, we are going to determine the equilibrium adiabatic flame temperature of methane. We have already determined adiabatic flame temperature for complete combustion, but this is equilibrium combustion, which means we do not know what the products are. The composition of the products are found as a result of equilibrium computation. The air we are going to use is going to be in theoretical amount. Also, we'd like to know if the air is at 90% or 110% of theoretical amount, what will be the equilibrium flame temperature? Well, we'll first set up the reaction and go about evaluating the inlet and exit states, and then determine the flame temperature by putting the condition that Q dot equals 0 for adiabatic combustion. So let's go and launch a suitable test step. Obviously, we'll follow the system analysis, open, steady branch, and combustion and chemical equilibrium. It should be mentioned that the combustion and chemical equilibrium right now works under pre-mixed combustion. So we go and one more thing, before we solve this problem, please make sure to go over the solution for adiabatic flame temperature with theoretical amount of air. And this is for complete combustion. And what we are going to do now, keeping this problem as a background, where we found the flame temperature to be 2329 Kelvin, right here, we are going to compare the result of chemical equilibrium combustion with theoretical combustion. Okay, so let's go launch the app, which is here. First, we pick up the fuel. There's no problem. 1 kilomole of fuel. Let's set up how much oxidizer we have. These are amount known. Equilibrium combustion with known excess or deficient air. We have 100% air for theoretical air amount. Notice the combustion is not theoretical, but the air amount is theoretical. Just to remind you, a theoretical combustion means carbon goes to CO2, hydrogen goes to H2O, and there is no excess air or fuel left. In this case, we still have theoretical amount of air, but we don't know exactly what will be in the products. So this will just make sure that the methane amount and the air amount are known. Now let's go and figure out the products amount. Well, not amount. What products should we include in our products mixture? Here's a list of all possible products made up of the atoms that are available in the fuel and oxidizer. A shortcut is just to select typical products that will produce very good value of equilibrium combustion. If you want, you can selectively include something else. So let's add all the typical products, about 10-15 products species. And as you can see, the reaction is now written as methane plus theoretical amount of air producing all these different species whose amounts are not really known. We go to the state panel. State 1 is linked with reactants. Now we have a premixed chamber. So we'll find the state of fuel and oxidizer at the same time, 100 kPa to 98 Kelvin. So this is our reactant mixture. And this is our products mixture, for which only thing we know is the pressure and nothing else. So we go back to the device panel and set up the reaction. So we have state 1 is our inlet and state 2 is our products going out. There is no work, there is no heat transfer. We click the calculate button, and that should produce the mass flux. We do a calculate here, and that should produce the temperature. And as you can see, the temperature is found to be 2223. It's about 100 Kelvin smaller than what we found for the adiabatic flame temperature for theoretical reaction, for complete reaction. So the presence of all the species, if you go back to the reaction panel, you can see the product species amounts have been found in the pie chart. All the different species have been listed, and the complete reaction, not complete reaction, the balanced reaction is shown here with different amount of even trace species of different compounds. Now, how do I solve this problem for 110% or 90% theoretical error? Obviously, it's a very complex problem. You have to redo the problem. Going back, suppose we want to solve it for 90% theoretical error. So we will go and reset. I would say the best thing to do would be super initialized and start from scratch. Methane is added, and we want to add, say, 90% theoretical air. We are just controlling the air amount here. So as you can see, air is less than before. And so fuel and air have been computed. Products, again, we will choose typical products, add those. The amounts are unknown. And go to state panel, calculate the reactant states, coming at 100 kPa 298, and the products we just know is 100 kPa. We don't know the temperature. Go to the device panel and set up the device. So I'm basically solving two problems given the complexity of the problem. I don't want to. In fact, there is no super calculate button in this particular app, as you can see. Come back to the state panel and do a calculate to complete the calculation. What it does, it takes advantage of the information from the device panel and then figures out the temperature, which is 2201. Again, you can show that the equilibrium temperature is less than the temperature we got in our last problem that we solved with complete combustion. There we got 2307. So it's about 100 Kelvin consistently smaller the temperature of the equilibrium adiabatic flame temperature. So likewise, you can show that if the air is 110%, you'll get a smaller temperature too than the corresponding complete combustion result.